Swayam Prabha. Digital India. Educated India.
Now, what we are going to do for the creation of this grid is that, firstly, we can simply discretize the bunny within the bounds. So let's say you have let's say for now, let's assume that there is an object lying in the space from 0 to 2, and I want to discretize this into a grid. So what I can do is I can take some delta, which will essentially mean how well I'm discretizing, and let's assume that this is a 3D space. So for now, yeah, it is a 3D space, and now what you can do is you can take some delta value along with which you are going to discretize or break down the space into pieces. So now essentially you have a discretized grid that you have obtained. So so in the x direction you are incrementing by delta x, in the y direction you are incrementing by delta y, and in the z direction you are incrementing by delta z. So once you have discretized this, now you have obtained a grid essentially. So you can use these as your grid points. Depending on the value of delta, you'll get a finer grid. So now in each case you have a small subcube. Note that all of these are 3D cubes because you're discretizing in a 3D space. Now what you can do is that you can calculate the centers of these cubes and use these as your query points. Now assume that you have a bunny somewhere here. Now you take the center and compute the distance and use these query points to compute the distance from the vertices of the bunny mesh. So assume you have some vertices of the bunny which are lying in these new discretized space that you have created. Now you use these query points to compute distances with the vertices. Similarly, let's say you have a query point here in this block, and then you compute a distance to this vertex, which was the closest. Similarly here, similarly here, similarly here. Is this part clear to everyone? So this is what we are going to do. We are going to split the space into a grid. We are going to calculate the midpoints. Then we are going to use these grid points so see, you need some point as a reference, right? So we are using a center point of every cube as a reference point. Whether the bunny would lie inside or not uh, in a particular cube would further depend on the query points as well. So these are just points of reference that we are using.
Okay, we can like choose any random point on the cube.
Yeah, you can use random points as well, but since we are aiming at a volume, we would want to create a uniform grid, right?
Okay.
So we pick the midpoints and use them as query points, right?
So if you take mesh of a bunny, then it may be possible that the query point that you are taking may not have an incident normal present in the mesh.
Yes. Yes,
In
there
that
is a
case,
possibility, and in that case, there is a method called a pseudo normals. So you can compute a pseudo normal for that point with which you don't get something for particular vertex and use that as a distance.
okay,
So
and so one more confusion is that the mesh we are having, and
so
we are
next,
trying to generate recursive bunny.
so recursive. What I meant by recursive is that so you get this particular shape, but it's like a recursive shape. You see this, where internally you get a similar shape from the sign distance field. Then in the outside also, it's just that the size of the and the amount of information in each level varies. Do you see this heat map sort of?
Yes, yes, I do see that.
At every level, if you see, pick just one color, one particular color, and then map the boundary of it. You will see that it is still storing the same shape information to some extent. Now, the level to which you will go, the amount of information you're going to capture will vary.
Right, right.
So, similarly, in the case of bunny, what will happen is that starting from the coarse side, so from the coarse to the fine, so you start from here, you create a distance field, it will look something like this. Then you create another field which will look like this. And as you move closer to the surface, the amount of information you will capture will increase, right?
Yes.
So that is what I meant by something like a recursive.
Okay.
So now let's take a look at the implementation. How do we actually do this in the implementation? So we first, what I've done is I've created a function called getCube. So what this getCube does is that it all depends on how well you can visualize, and if you can visualize things well, you can quickly type it up into a numpy array. It took me hardly 15-20 minutes to come up with the logic to create breakdown into grid and complete this whole process. So let's take a vertex set for a cube. So now we know that we want to create a cube from a given set of vertices, and this will be some discretized cube, right? Okay, I don't need to name the vertices. Let's take this point to be my coordinate xyz. Say I'm beginning from the grid here. So let's say I start from here. This is my point xyz. This is some arbitrary point. And now I need to create a cube from here to here with each size is delta, right? So what kind of vertex set I'll get? If this is my xyz, and let's assume this is my y, this is my x, and this is my z-axis. So I can take it to be like this. And now this point here would be something which would be delta x. The rest of the coordinates are going to be the same, so I'm not mentioning those coordinates. This one will be delta x, delta y. I'm talking about the increments in each of these directions right now. This one would be delta x, delta z. This one would be delta z. This one would be delta y, delta z. And this one would be delta x, delta y, delta z. So these are the kind of increments I'm going to need for any given vertex. What I've done is that I've created a function getCube. So it takes 3 points x, y, z, and it returns the cube that will be created from the selection of this vertex set. Is this point clear? Is this step clear to everyone? Just add a +1 or just ping in case of any doubt. Because this is essentially, this is how we're creating the unit here. And then we are going to replicate it across the entire space. Okay. So once I have this cube function, what I can do is now I can calculate the bounds of my bunny. So in order to do that, I can simply take the min max. In this case, there is no condition that it should not be touching or this should be touching. So I've just simply taken it up as min max as it is. Otherwise, you can still create a bounding box and do that business as well as we have done in tetrahedralization. But right now I'm just taking the min max as it is and creating a bounds list. So this will basically create, this will decide how big my, so this will essentially decide the size. So this will be x min, y min, and z min. So this will be the origin that I'm going to treat it as, and the bounds, that is the this point here. Let's say if it was a cube, it was a big 3D cube. This one would be my x max, y max, z max. So now I'm going to distribute it into all these subcubes from x min, y min, z min to x max, y max, z max. So this is the logic for creating a grid. I take the minimum bound, I take the maximum bounds. Now I see the number of subdivisions that I'm going to get by dividing the difference between the minimum bounds and the maximum bound by the delta, adding it plus 1 and rounding it off just to take care of the bounds. So this will essentially tell me how many elements I'm going to get in x direction. Xb is the number of x divisions. Then we have y divisions, yb, and similarly we have z divisions. Oh, sorry, z divisions, and these are the y divisions. Right, so once we know how many grids we have to traverse through, how many cubes we have to traverse through, now what we can do simply is that we can start from this point, increment by delta. So essentially I move by delta in x direction, then I move by delta in y direction, and I move by delta in z direction. Also note that you're taking this point as your starting point to create a subcube. So when you reach the topmost point, you have to stop at this point, because at this point you will get all the subcubes that you need. There is no subcube for this particular x max, y max, z max. Kindly note that, because that's your limit, that's the bound, right? There is no cube outside of this. So you stop at one point below. So this point would be x max minus 1, y max minus 1, z max minus 1. And you use that because when you increment it by delta, you will incorporate this maximum point as well. So that is why, if you notice, there is a minus 1 in this number of divisions as well. So I stop one division before, I pick the topmost point and I calculate the bound as well. So now for each of these cubes, we need to calculate the center as well. So once you get the cube points, you can simply calculate the cube mean, and that would give you the coordinates of the center point. Once you obtain these cube points, we are nearly done with the discretization part. All now we need to do is, now we need to take these cube points or the cube centers and use them as query points to compute the sign distance field. Any doubts so far? Okay. Just let me know if you have any doubts. Should be pretty straightforward. This is just visualization and coding it out. So once you do that, you get a center as well. Now what I do is I just reshape it back in the shape of the bounds that I had. And now I'm going to use this to calculate the sign distance field. So IGL provides you with a function sign distance field. I take the center, which are my query points, and compute the distance from the vertices and pass on the faces as well for the bunny mesh. So this returns three values. One is the sign distance values, then comes the points for which we had calculated, and some more information. The zeroth tuple essentially contains the sign distance values. So all you need to do is you need to just reshape it back in the shape of the grid that you had created, and then you can simply visualize it. Can you see this? So this is coarsely showing you the bunny from the front. Uh, if I also plot the VNF. So if you see, this is the front and this is how the bunny looks in terms of sign distance field. Is it visible to everyone? This is the bunny and this is the course shape that you get. So essentially you have created a sign distance field and you can just plot it and view it. So this is a slice. Now notice that earlier mesh was in a continuous space. Now this is a discrete space. So you essentially discretize your bunny mesh into a grid now. And this is the shape. So it is a grid of size 26. Can this be visualized in 3D? Yes, you can visualize this in 3D as well. However, note that this is solid volume. So when you look at from the outside, it will be filled, right? So essentially you pick a slice and then see. Otherwise, if you look at the grid itself, it is just a colored set of cubes. So if you look at this in 3D, it will just, you will only see RGB colors in each of these blocks. Are you getting? So you might not be able to actually understand what you have plotted. So what you do is you pick a slice from that 3D volume and then see. Is the doubt clear now? Soma. Okay. So you take a slice and then visualize it. But essentially now what you have is a discretized grid which is closely resembling to the object. Now comes the part of verification. Now you want to verify some way that the grid that you have obtained is correct, right? So there's an algorithm called as marching cubes that you can do. And what it does is that it will help you convert this discretized grid back into a mesh. And that is, if that mesh is the same mesh as the bunny mesh, then you know that your sign distance field is correct. Because the zero level set, as we had seen before, should be the surface of the mesh. So scikit image has something called as marching cubes. So I'll just show you what essentially marching cubes looks like. So this figure basically is a coarse representation of what happens in 2D in marching cubes. So you had a grid and that grid had different values. So essentially you pick the cubes that have that particular value and you convert them into triangles and you step along and you essentially march along the surface where you get a particular value, which we call in our case as the ISO value or the value that the particular contour will be contained. So in this particular case, since we had already obtained a discretized grid, now what we are going to do is we are going to take this discrete grid of sign distance value and do marching cubes on it on the zero level set. So this is important to note that we are picking the zero level set here to perform marching cubes, and that essentially should give you the surface that is holding those and that particular ISO value. So when you do marching cubes and obtain the verts and faces, then you'll notice that what you get back is the same as the bunny mesh. It should be coarsely close enough to the bunny mesh. Depending on the kind of discretization we did, the amount of information could vary. So let's reduce the delta to even a finer grid, and I think it should capture even more details of the grid. Yes, that is some reconstruction error, and it depends uh, on the kind of discretization you're doing. So now if I reduce my delta, I create even a finer grid, it should capture even more values and it should be finer when it comes to the reconstruction. Now, if you notice, the holes have, some of the holes have closed, some of the holes are still there, but it essentially depends on how well you create the grid and how well you created the sign distance field. However, this is a simple check that you can use to check whether or not the surface that you created is correct or not. Because when you are actually doing some discretization, there is obvious loss of value. So you're not able to capture to the extreme details If you notice, there are some really fine details in this particular region, and this is where the maximum information is getting lost. So if I pick even a finer grid, I might be able to recover those details. Also note that if you remember, we had seen that the number of vertices in the bunny mesh was in the order of thousands. But right now, the size of the grid is just 39 cross 39 cross 30. So this is a very small grid if you compare it with the amount of information. So essentially, every point is storing just one value. So there's a tremendous loss of information. However, still we are able to recover back the original shape to a great extent. And yes, I guess with this I would like to close the session. I hope it has been informative for you. We can quickly take up the questions for the next 5 minutes. Otherwise, feel free to leave.
So last day on class, when I asked Rojaswa sir regarding the sign distance, he asked that we use the sign distance to make the basic structures, and after that we perform Boolean functions to create complex structures. But here the thing that we are getting means where are we using the sign distance field? Like in where do we apply this?
So in the case of voxelization, you would need a sign distance field. So let's say, do you know about voxels and voxel volumes? I'll
Uh,
show you some.
what I assume till date is that if level where the level set is 0, within that queue, if it is filled more than 50%, then that will take it as 1. Otherwise, I'll make it 0. I had this assumption.
Okay. Okay. So there is a paper called as Deep SDF, perhaps. I would want to take a look at it.
Yeah, I think the question is more on kind of Boolean operations that were shown in the class. Of course, Aradhya did not show them. The idea is basically you can merge two objects, you can intersect two objects if you have distance fields of both these objects using simple function operations. Was that your question?
No, it wasn't my question, sir. Like yesterday, sir showed this thing that we are using few simple structures. We can make a few complex structures by performing Boolean operations on that. So I
Right.
thought that the signed distance is for that purpose only, in order to generate.
So see,
Complex
one of
structures.
the greatest advantages that you're getting out of a sign distance field is the kind of representation you're using.
Okay.
You can actually use a continuous field to represent your surface. So even if the bunny mesh in itself is a discretized, depending on the kind of field and the delta value that you pick, you can actually create a very continuous surface, so to say, with respect of that. So that is how it is quite helpful with you for you. So and you can quickly, as Aditya sir pointed out, that you can quickly perform operations on sign distance field. So even if you look in our case, earlier we were storing all this information in vertices and faces containing like 10,000 vertices and so many faces. But now we can simply compress this information using a sign distance field, and to some extent it helps us capture the nitty-gritties and the kind of information that a particular voxel volume would hold.
Depending on our delta.
Yeah.
And one last question I have, what this mesh and face that you are using as a data structure, what all things do you use when you do perform deep learning structure on it? What all types of architectures do generally deep learning?
I see. So, see, there are different things depending on the, because in case of deep learning, the kind of data you're going to work on matters a lot. So, if it's a voxel based data structure, if it's voxel based, then I would go for 3D convolutions or sort of something like that, because you have a grid, right? So, you can treat it like a 3D image and perform 3D convolutions on top of that. So, I'd go for 3D convolutions in that particular case. Say I have point clouds. Now, in case of point clouds, what I would want is that inherently there is no grid-like structure, right? There is no connectivity information, something like that. So I would want the network to recover that sort of information from the data itself. So in that particular case, I would go for something like on 1Ds. I perform 1D convolutions along the different channels where I treat my dimensions as different channels. So along XYZ coordinates, I will be performing convolutions and creating embeddings of those sorts. Then comes if it's a mesh data structure. So now if I have a mesh data structure, I would be inclined towards geometric deep learning. I think there's a different session on top for this as well. So in that particular case, I would focus on not only the vertices, but also the adjacency information. That is the core that we focus on when it comes to the meshes. So if I need to focus on this particular function, I'll be using Laplace operations or Laplace-Beltrami operators to define a function that can be operated not only on the set of vertices but the adjacent edges as well, because there's some connectivity information lying in that particular region in case of meshes. But if I have to perform some operation on point clouds, then there is no connectivity operation. They are just points in 3D space. Similarly, in case of voxels, there is some connectivity information. There's an 8 connected neighborhood that you get. So a voxel representation is something like somewhere in between mesh and point cloud in terms of information. It has some connectivity information and it has some information that is being stored at that point, which is captured in terms of intensity. Right? And when it comes to meshes, right now we're talking about 3D meshes where you're talking about only vertices and edges. But if you if you talk about it in a generalized sense, it's nothing but a graph, right? So instead of a vertex where my feature of a particular node is a set of 3 values, it can be something else. Similarly, my edge can be represented as something else. So you get a very complicated set of adjacency matrices and the vertices, so to say. And similarly, depends on the kind of task you're performing. If you're performing some sort of reconstruction, then you would be inclined towards autoencoders and GANs. If you're performing some sort of classification, then conventional CNN kind of loss function would be sufficient. However,
I was thinking like something that for this, it should be applicable to 2D or 1D data also, but for 3D, I was thinking like that if we could compress it using autoencoder and from the latent space, if some data gets attenuated on getting transferred, could be regenerated on the receiver side so that
yes.
a self reconstruction error could be imposed on it and
Yeah,
something like
there
that.
are tons of papers along those lines. There are variational autoencoders that perform point cloud completion. There are GANs that perform point cloud operations. However, one of the biggest difficulties that generally people come across is the number of vertices that each of these meshes have. So conventionally, as you've seen, they have like 20 to 60,000 vertices, and this is on the lower end that we're talking about. If you pick something really complicated, like a mesh of a complicated architectural structure like Eiffel Tower or something, it can blow it up to like millions of triangles that can be accommodated in a mesh. So that becomes a big problem. That is why people often, when they talk about uh, deep learning based operations, either they perform some sort of decimation on the meshes so that they can control and scale it down to some sense. And similarly, in point clouds also they perform clustering and then reduce it up. Voxel is more suited, however, it also bloats up because beyond 64 cubic volumes, there is not much information that you can store, but the memory requirement blow up very fast. So even for a 128 cubic volume, you would require, even for a batch size of 1, you would require a graphics card that can fit up to like 12 gigabytes for a conventional deep neural network with 3D convolution.
So college server fits for that, right? Hopefully.
Yeah, it's difficult to put on college servers.
It will fall short of that. Our
Yeah.
college server.
So you can use a 64 cubic volume. You can downsample and then use it. I think in that case you can fit. Otherwise, you would want something like DGX to really run at its full potential.